Hello, I'm Hayley, and this is another presentation I prepared called Techniques and Utilities for Farming Objects on the Net. It's a sort of follow-up to the lightning talk I presented at the European Lisp Symposium in April, because I thought it was quite short, quite rushed, and I just didn't think it was very good at describing what I was working on at that time. As well as that, someone asked me to prepare a presentation for the Online Lisp Meeting, so I decided that would be quite interesting and would be quite useful to create such a presentation. So Netfarm is a multi-user distributed object system, which is sort of a kind of distributed storage that stores objects and can do a few things with the objects. These words, this distributed object system, I'll just give a pen for later. This sort of distributed object system is a word that means a few things depending on your use case, the implementation language, although we want to be quite portable. It is still usually based off the implementation's language object system. So we're going to describe what this means for us. It's a class-based object system in which we have objects that are instances of classes or schemas in this case, because to us they sometimes act a bit more like data than objects. But they are classes in a sense. Furthermore, it's possible to create such schemas as well as part of a separate program, as part of a separate protocol. So it is possible to extend Netfarm in this way. As well as this, the objects are represented in a way that makes the data type sort of obvious, such that we have references that are actual references and not strings that store hashes or anything like that. We have actual reference data types. And of course, objects being instances of schemas. With our client library, we also decode the schemas into Common Lisp classes and then have Netfarm instances be Common Lisp instances. So it's very much an object-based system. As well as this, it's distributed in a networking way, where the load of running the Netfarm system is spread across many servers or nodes. As well as this, we also try to spread it out in a way such that there's no central point of failure. In this diagram I have, I guess, some kind of network diagram where a client may have connections to these two nodes. These two nodes also connect to that node, and it's possible for a client to discover that node should it need to. If one of these nodes were to go down, then we could, if one of these nodes were to go down, such as this one, then we would still be able to access the resources represented by these shapes. This one still has the red triangle, this one still has the circle, and this one still has the square. So with that out of the way, we can look at the other features of Netfarm. We use digital signatures and hashes to ensure the integrity of the objects submitted to the network. We use signatures to make sure that the author of the object is actually the author, as it's not, I shouldn't say not possible, but it's very, very difficult to create a signature without having the requisite cryptographic keys to do so. So it would be difficult for someone to pretend to be someone else on this network. As well as this, we also use a hashing system to, of course, verify that the object is intact, and to address the objects. When we ask a node for an object, we ask for it by its hash. To do some kind of side effects after all this, we use a sort of actor-like system, which allows us to run our program reproducibly to create side effects. It's also an experimental system. We originally used it to learn concurrent programming and how to do that well, And now we sort of use it to test out a few new ideas, which I'll describe in this presentation. If we've done it right, then Netfarm is also quite extensible and reusable. We have separate object serialization, networking, object storage components, and so on. These all have comprehensive protocols so that you can replace any component of it separately and keep the rest. As well as this, there's also a bunny. I know it's not really relevant to an online Lisp meeting, but someone said it was really important, so I decided to keep a slide for it. Also, so that Fee can use it for the thumbnail for the video when they upload it to YouTube. So the Netfarm is about the product of about 3 years of messing about with object systems. The original incarnation of Netfarm was this system called BlobNet, which was just a little synchronization networking hack that I did in Python to experiment with the idea and see if it was feasible. At this point, my goal was to create a kind of distributed form system for a specific corner of the internet. From there, I decided that it could be quite doable, so I started to work on a system called nettle in Python, as this says. Since from that, I kind of came up with the idea that a system should be very extensible, and due to external factors, I also decided that we also wanted a distributed system in terms of our users as well as our nodes, that we shouldn't have any central dependencies on people even. So while that was quite interesting, and from my point of view, the most people were interested at that time, we also found that it was slow, so we ended up learning Common Lisp and ended up porting Nettle to Lisp at some point for a short period of time. But then we figured out the semantics were kind of not really sound, and we decided that we needed to put that to rest. So for a brief bit of time, I just kind of learnt Common Lisp without doing anything, and then eventually I started working on a new system called Netfarm, named after the server which we had used to test Nettle on. The first component that I worked on was a networking library called CL Decentralize. This also would eventually be redone, but for a short time it sufficed, and we were able to get Netfarm talking with it for a while. After that, I started working on Netfarm, the object system, and about halfway through its lifetime, about near the end of 2019, we integrated it properly with the Meta Object Protocol, which, as well as that, around that time, I also picked up a new networking library based on shortcomings of Decentralize 1 called CL Decentralize 2. And since then, we've written some networking code to glue the two together and create a proper Netfarm node system. As well as this, there have been 2 small releases, if you can even call them those. I don't really want to call them those because I wouldn't really suggest using either as it stands. They're just kind of markers of when the semantics of the system changed sufficiently. I'd say that before 0.0.1 the system was definitely different to how it was at 0.0.1. Same with 0.0.2. And unfortunately, 0.0.2 was made not very long after the European Lisp Symposium. So there will probably be a few statements and a few slides that actually contradict what I said at the European Lisp Symposium because the system has changed. With that out of the way, we should be able to start talking about some of the interesting stuff in Netfarm. With the Decentralized 2 system, one of the things that we really want to improve on was our dependence, or rather independence, on the networking protocol, the wire protocol. Our reason to do this was quite silly, so instead I'm going to possibly describe it using a more interesting example. For this, I'm going to look at a project that the Matrix developers did. Matrix is a kind of not distributed, but decentralized messaging system, a bit like IRC, or Discord in terms of features. The specifics of the system don't really matter to this, but we need to know that there is some kind of client-to-server protocol. This usually is a fairly web-y, if you can use that as an adjective, a fairly web-y protocol stack. We have objects represented using JSON. Those are sent over HTTPS, and of course HTTPS communicates over TCP/IP. Well, for now, I'm not really sure what HTTP3 is doing, but for now it runs over TCP/IP. This is a bit slow if you have a really slow collection, one with very little throughput, specifically on the order of 100 bits a second. So what some Matrix developers did was that they developed a proxy, or a pair of proxies, that would sit in between the client and the server and intercept any messages and re-encode them in a more compact object representation, the CBOR, with a collection of more lightweight and more dense encryption and datagram protocols. And with all this, they achieved a 70 times reduction in object size, which is quite impressive. While they did that very well, the architecture of using a proxy stands out as a bit weird. Of course, one of the things that we could talk about is how there are multiple unnecessary serialization and deserialization steps. We can count these. At the client, we're going to encode the message. At the first proxy, we decode that and encode it in the compact representation. At the second proxy, we decode that representation and re-encode it in the web web protocols. Then the server decodes that again. Now, we can't really complain about this because at 100 bits a second, almost anything would go. But if it wasn't 100 bits a second, and we want to experiment with a different protocol for some other reason, then this could be quite annoying. Of course, serialization like this, these additional steps, take time. We'd like to be able to eliminate these, so we'd like to not have these steps. As well as this, having these separate proxy processes is also a bit strange, depending on the language implementation. This could mean that it takes up additional memory, additional resources, and on some devices, like some mobile devices with sufficiently walled gardens, as they're called, we could imagine that they might not even be able to, say, bind networking ports to run this proxy server on. So in any case, we'd really like to be able to eliminate these proxies as well, and just have some component of the client and some component of the server be able to use these network protocols interchangeably. So when we did this in Decentralized 2, we eventually settled on a protocol that basically involves, 2 degrees of freedom, 2 degrees of independence, 2 different stages of representing and sending a message. So if we were to look at how a message is sent from a client to a system, a server, or anything like that, we could look at it in we could kind of trace it down on a diagram like we did for the matrix system. So the first step we have is that the client... No, we're not going to start there actually. We're going to look at it quickly, just go over it. We have a few components. We have a client which is going to implement the logic of handling the requests that the outside program might use. As well as this, we also have a representation of the connection as well. We have a sort of abstract protocol for connections. This one may use a TCP socket as an example, but you can use any other connection, such as we could use UDP. You could use a serial port. You could say use Tor or do that. You could also use a tin can and a string if you're trying to be funny, or anything like that. As well as that, we also have 2 translators. What the purpose of a translator is it takes an object and serializes it, and then the same translator at the other end takes serialized form and deserializes it. So it's just effectively all our translator system is a funny name for basically having a table of connections and object representations that we might need to marshal between. So we can try and trace down how a message would be sent. First off, the client would send the object representing the message to the translator. And what the translator does is it takes the data portion, basically the payload or the object that we're trying to send as part of the message, and it will turn that into a serialized format, which is usually a vector of characters or a vector of bytes. And then with that, the serialized format will be handed to the connection as part of a message, and then the connection will decide how it should send that off, and sends it off. Then it goes down the wire, and the other connection passes that message, and oh dear, we've gone across the page. We don't want to do that. We're going to go back now, and keep going with this without performing any time travel this time. I don't know what it is with this mouse. Why does it think I'm right-clicking? Anyway, the connection passes this message and decodes it. And then this message is handed to a translator, which then looks at the data, looks at from when it came. That's one thing that the translator can dispatch on. And it will also look at where it's going. So it will pick the format that's appropriate for the system. Then the translator will decode this, and it will be sent to the system. Furthermore, we could also imagine that a translator could also be used to serialize the object and store it in a database. In our case, well, we don't really use a translator for this, but it could be doable. So we've included this to show that the translator system is just agreed upon convention for how we should encode and decode our objects in a polymorphic way that allows us to use many different system types and many different connections. As well as this, we can now look at distributed filtering, which was sort of spoiled when my mouse decided to do that thing. So filtering, also sometimes called moderation depending on where you are, is usually done in a sort of centralized manner, or sometimes not even done at all, on even some decentralized systems. Looking at the examples we had before, some federated systems have the filtering done per service, such as Mastodon and ActivityPub. Some have it done globally, like Matrix, although it's not really globally. It's done per room, but it's done across all the servers, so it kind of is globally, but it also kind of isn't. We'll call it globally for now. One of the problems with this is that you don't really know if you can trust the moderators. This is part of your threat model, and your model of how you trust the people, and sometimes you don't trust them. And sometimes when you do trust them, they turn out to be really terrible. And this quote by philosopher Mikhail Bakunin kind of expresses that in very concrete terms. As well as this, if we had one large distributed system, specifically a very large one, in which we may have thousands, tens of thousands, so on, users, it might be tricky to have, say, system-wide votes or consensus or something like that, because we have enough people that we'd have many dissenting opinions and we might not be able to get to a conclusion anytime soon. So instead, we're going to take one from Usenet and some systems like that and try to do all our filtering on the client side. The main benefit to this is that we have no obligation to produce the same results for every user. We don't have to come to a conclusion. So we can approximate what the user wants really well. And approximating what the user wants, or at least what we think they want really well, is something that has been studied for quite a while. And this encourages a kind of this encourages groups that want to do things like targeted advertising to try and study doing filtering systems that don't require people to step in. We can use there are several statistical models we can do for this. And these all fall under the banner. These all fall under the banner of collaborative filtering. We're going to use a simple version of it, just to simplify a few things. Like, we'd like to be able to explain it. We'd like to be able to reassure the user that we're not doing anything particularly fishy with the data. Say if we were to, pass it through a neural network or something like that, the user obviously wouldn't be able to disassemble what that is doing, and could be quite confused as to if the neural network's actually doing what's supposed to do. So using a very, very simple statistical model here. So the way we can represent a problem like this is that we have several users. Like, here's me, here's two of my friends, and we have an abstract kind of fact that represents each thing we need to make a decision of. And in the end, we'd like to say if they're true or false. So it might be, do we think this object is spam? Do we think it's relevant to this topic? And so forth. So we can try to estimate it. We can try to estimate any missing facts like this one here, this one here. To do that, we're going to use a two-step process. The first thing we're going to do, which is sort of this first equation here, is that we're going to produce correlation values. The way we do this, firstly, is that we need to pick a user that we want to get a value for. Say we'll pick Gnuxy for this one, and we're going to pick all the facts that we've both decided things on. So it's these three. We've already given away the value, but we can step through it anyway. We have these three facts here. And if we were to represent every fact that we think is true with the number 1, and every fact that we disagree with the value of -1, what we can do is we can multiply these values together to get 1 if we agree with them, or -1 if we disagree with them. Then if we sum all these up and divide by the number of rules that we have in common, we'll end up with a correlation value. So here we have 1 that's agree, so that's 1. We have 1 that's disagree, -1. And we have 1 that's an agree, so that's another 1. Add them together, we get 1. And then should we divide it by 3, we get a third, like this one here. We can do this again with our other friend here. And we see this time we only have 2 rules in this case, and we both agree, so this is just going to be 1. Now we'd like to be able to predict and fill in this value. So what we'll do first is we'll select all the users that have already filled in this box. So we have these two here, both of them, and what we'll do now is we'll multiply the values assigned for these with their correlation value. So we have a 1 for this one. So here we say that we have a value of 1/3. I regret not putting this in the presentation animation, but that's okay. And here we have a -1. And there's a weird line that I don't remember putting in the presentation as well, which is really strange. LibreOffice has been really strange the past week, but we're going to deal with that. So we have a -1 here, multiplied by the 1 correlation, we have -1. Then what we're going to do is we're going to add these together, and we have -2/3. And then we're going to divide that by the sum of the absolute values of the correlation to normalize that to the range -1 to 1, which is what we've been working with. If I divide that, then we get a value of, I need to actually write this down. We have -2/3, and we're going to divide that by 1 and 1/3. So we're going to go 1 plus 1/3. That's 4/3. So we have 2/3 over 4/3. We can get rid of the thirds part, so we get 2/4. well, it's actually -2, by the way, -2/4, which is -1/2. So we're given a value of -1/2. And we can interpret this as false if we like, or we can but we better interpret it as a fuzzy value. And this fuzziness is quite important, and then we'll see that we can use it in a sort of ranking system with... Oh, that's gone. I forgot what I did with the animations on this. Well, we can see that we can use these fuzzy values to drive a ranking system, such as the one in this demonstration. So here we have Emacs open, and I have loaded already. I've already loaded a recommender demonstration program that I've written before. So what we'll do is we'll just run this firstly. What we'll see here is that the program called the Netfarm Interactor kicks up, and we'll see that it's just started it started up with its default page. We've modified it quite a bit, and we'll show you this in a bit. What we have here is we have a little program here. What we can do here is that you can say of course you can read the presentation of this object that we started with. This is an object, and we can click on the object hashes here to look at a different object. So what we can see here is that we have another object, and if we choose to, we can also inspect the schema, the class of it, and we see here that we have some slots. We have some weird values that are default and don't really mean anything. We also see that we have a little script, a program that produces the presentation. This is just a short program that we interpret, that basically copies a slot called presentation. You don't need to understand this to understand Netfarm. We use an assembler, or sometimes even a small scheme compiler to write these programs usually. But you can be assured that this will read off the current object. This bit here will get that presentation. This will take the slot value. This will return it. Going back to the introduction, we can now look at some of the features that we've actually added to the system. What we have in mind for this program is that we want to categorize some news articles, kind of like you would do on a forum like Reddit or Hacker News or something like that. So what we're going to do is we're going to type in a command to look at such categories. We're going to go inspect category. We'll start with Lisp for this one. And we see here that we have some names of the articles, and we have some links to the articles. So we can look at it, and we can click it. Oh, that sounds really unfortunate. Go back. We can just keep looking at this. So while this is all good and all, we'd like to be able to order these as well, or possibly even filter them out. What we'd like to do is we'd like to put the most relevant topics at the top and the least relevant at the bottom. Depending on the system, you might even want to filter them out, as I tried to say before. But in this one, we're going to keep them all here because writing the presentation program was already tricky enough, because my compiler is still a work in progress and it doesn't understand some of the constructs that I wanted to use to make this. But anyway, what we can use to start to order these is that we'll use a sort of triple store system, which means that we have a database somewhere of facts, like I was mentioning before, and these are written out in a very... These are represented in a very simplified and very... what's the word? These are represented in a very simplified and... I can't think of the word, but like they're represented they're all represented in a very similar way. We'll see what they look like right now, and we'll start to classify them. We'll say we want to add a fact to the system, and we'll say that this one here, this article here, the subject, is relevant to this category Lisp. And we'll just put that in. And we'll see that the collaborative filtering system that we've added has decided to put this up the top, because it's the most sure that this is definitely relevant, because after all, we said it was relevant. Now, we can keep going like this and classify the rest, but we'd prefer not to, and we can begin to use this collaborative filtering system. Supposing that we had extended this system such that, say, if we kept looking through the articles, suppose there were users on it, we could collect the databases of the users in the background, supposing they make those public to be collected. But suppose we've collected it, and we have a command that lets us list the other users in the system. Should we do this, we're presented with a list of the other users' databases, or user maps as they're called, and a correlation value that we've already computed. We can go ahead and inspect these if we want to. We can see it's just another object, and we have this triple store representation of subject, verb, object, and so forth. There is also some stuff about mutability, and these are also handled by scripts, but we're going to get to those later. Going back to our category, we can say, add this person as a delegate. We want to delegate the task of filtering this to our friend Noxie here. So we're going to do that, and we'll see that it's sorted some more. We see that these two that are probably more relevant to Lisp are up the top, and these two, which are unfortunately not relevant to Lisp, are down the bottom. Now, if we add some more, we can add some more of these. We can say that we can add some more information. We can also tell the system that we think something is false. I couldn't find any better antonyms for the word fact, so I had to use the word lie, which is really funny that you tell the computer you're lying to it. So we'll say that we don't really want to know about this because that's really sad. So we're going to say that that's a lie, that it's relevant to Lisp. And it's really unfortunate, and that's really sad. Moving on, we can say that it's acknowledged that this is definitely the most likely to be bad, because we just told her that it was. If we list the other users, then we can see that in fact we've made a decision that Jaden doesn't agree with. And because we have one that we do agree with, and we have one that we don't agree with, then the correlation value ends up being 0. As mentioned before, this value can be negative, and it means that we're more likely to disagree with them and not. And we can still actually make use of a value like that. So while we have this fairly useful collaborative filtering system, in some cases we might want to try out a different system. So if I look at another category, well, this one's about pets. What we see here is that we have a kind of story happening to some extent. First we have a study finding that vacuums pose no threats to pets. They probably shouldn't have put that in the title. Then we find out that someone's budgie is being eaten up by a vacuum cleaner, and then they made it out okay. So for this, we'd like to have the newest and most accurate information at the top. We can represent this with another relation that we can say that one of these some of the information in one of these articles supersedes information of another. Say if this is obviously false if a vacuum cleaner sucked up a budgie, but then they made it out okay, so then it's not really so much of a problem. This other one here, that's an in-joke that you probably won't get, because that's really old in-joke actually. I can't remember when that was. That's the one we decided we wanted a bunny mascot, but that's not relevant at all, so I don't really mind where that one goes. To do this, we're going to change the recommender system. The recommender is the object that sorts these that sorts the articles in a way such that we think the most appealing will be at the top and the least appealing will be at the bottom. To do this, we want a kind of a topological sort, but it's not really topological sort because we're just dealing with probabilities that any of the relations are true. So in some cases, it can contradict itself and say that one article supersedes the other, and that one supersedes the first one, and we wouldn't know what to do with that. So if I close this and I change the class of the recommender to a collaborative sorting recommender, then we can start looking at sorting. So I can just show you the code for this. I could probably have written it better, but put simply, what we do is we use a process of simulated annealing to try and approximate the best solution that minimizes the number of mistakes that we've made in our ordering. We want our ordering to have the least probability that we've put an old article at the top and a new article down the bottom. So we just produce a list of relations, and we tell simulated annealing process to try and minimize the number of relations out of the wrong way around. And then at the bottom we see that we sort the object list based on these relationships. With this, we'll just go back to the REPL and we'll run the demo again. Now what we'll see is that if I go back to pets, we'll see that the ordering may or may not be correct. Actually, in this one, we will lucky it is correct. But if I click on this to refresh it, we'll see that it's randomized. And this is because that the simulated annealing is a randomized process, and we just keep swapping it around. Did I reset the recommender or not? Actually, it could be. Actually, yeah. It is the right way around because I've reused the user map and the delegation from the last one. You can see that is still a bit randomized because this could go anywhere, and we don't really mind where it goes. Ideally, we'd probably put it up the top if it's still relevant and there's nothing wrong with it. We could do that. But if I were to close this, and if I were to reset the recommender, and then inspect the category pets with no information, it will just be entirely randomized. So we've seen a practical application of this collaborative filtering. And we've seen two recommenders, one that just uses filtering outright, and another that uses it to produce a set of relations that we try to sort the inputs on. We will also notice that we've implemented them in fairly different ways. So it's not really trivial to combine these two, and that's something that would be interesting to think about. So, with the fun stuff out of the way, we can look at concurrent programming. When I started learning Lisp in order to make Nettle go faster, I was quite impressed that I could make it run on multiple threads and use all the resources of the computer I was running it on. But the fact is that concurrent programming is actually really hard, and somehow everyone can do it better than Python can, which is strange. But you know, that's scripting languages and all. So when we want to make these things go fast, we need multiple threads, as previously mentioned. And in Decentralized 2 and even parts of the Netfarm server itself, we find a need to store a lot of things in hash tables. Some hash tables, though, only assume that they're going to be modified in one thread, which are most hash table implementations. So the easiest way to make multiple threads be able to use it without bumping into each other is to put a lock, a mutex, over it. And to do this, we had kind of devised a little container type, a box that would allow us to unlock it and grab the lock, and modify the value of the box however we see fit. However, when we started to parallelize the system and make some of the steps involved in synchronization and all that kind of thing concurrent, we saw there was contention over this because one thread would lock the table while it does one modification, and another wants to read from it, and they wouldn't be able to do so concurrently. So the first thing that we looked at was to create a simple concurrent hash table based on the one that Java has, the concurrent hash map. The way that works is that it basically delegates all the storage to several smaller hash tables, which are dispatched based on the hash of the object. So, say all the hashes ending in 1 would end in 1, and all the ones in 2, all the ones in 3, so on. They'd all end up in different tables, and you'd be able to lock all those separately. In the end, this turned out to be a really happy coincidence, because I also sometimes contribute to Sickle's hash tables. I can't really remember if I ended up working on hash tables after or before I did for decentralized too, but I'm pretty sure Sickle was after. But there aren't any concurrent hash tables in Sickle, but there will be in a bit. But a thing like this only scales so far. We're still locking, and we could just keep throwing more hash table buckets at it, but that would get quite large, and we still have to lock anyway, so it's quite slow. So I've also looked at a non-blocking hash table, such as the one written by Cliff Click Jr., which is also in Java for some strange reason. Nicola Hafner also did a port of this called Luckless, which we've also made a couple of changes to in order to try and increase the performance of it, with the eventual goal of being able to address that from the concurrent hash table library as a different implementation of it. So we can put the performance change of concurrency and concurrent data structures into a diagram format. So what we have here is that we have some timelines generated by the Clim Flame Graph program that that basically generates these sort of timelines as well as the flame graphs themselves. These timelines are nice to look at because you can see times when the threads are stopped, like here, all of this. And you can see where the threads are running. And you can also sometimes even visualize the contention, like how these spots get a bit patchy, and same here. But anyway, we can see as well that when we used to do things serially, we found, well, obviously it was a bit faster, but but we had this huge pause of about 1.5 seconds while one thread was doing all the passing. Nothing could be done. When we moved this to a concurrent data structure, we found it to be a bit slower when we started to... Well, actually, we didn't use a concurrent data structure, we used a locked structure. And we found it to be quite a bit slow. We can see that we delegated one thread to passing an object that's being passed around a decentralized to. This was very slow because we're locking and unlocking it for every operation we wanted to do on the table. And in the end, it turned out to be a bit slower. However, we do see that we've sort of minimize the latency until we really get going, which is very nice. But still, we've gone a bit slower, and we can see that there's some contention here, so it wouldn't scale very well if we had more connections even. After that, we introduced our first concurrent hash table, and we ended up getting the benefits of both. We had very little initial latency before we start synchronizing, the green line here. The parsing process was still quite fast, about as fast as it was when we were doing it serially. This is about 1 second or so. It's been interrupted by the garbage collector. It wanted to step in for a bit. But otherwise, we've even made it a bit faster, as we're able to retrieve information while we're still parsing. Since then, we've also made a lot more changes to make it more concurrent, and about now, this process now takes about 4.5 seconds. This synchronization test that we do only takes about 4.5 seconds on my machine, which is about half of what it used to when it was serially, so I've achieved quite a great speed up with that. Now, as well as being able to make fast concurrent programs, we want to make robust concurrent programs. The problem with this is that programming is hard and we probably messed up, so we want the computer to try and be able to fix that for us while we're busy doing other things like sleeping, doing homework, going out on vacation, all of the above, because sometimes it is like that, and anything like that. Anytime that we can't be around the computer, we'd like for it to be able to fix its own mistakes, and we'd also like to be able to be as far away from the computer as possible at times. So, say we have the case that one thread decides to disappear. What could happen then? The system could run a bit slower if we have a thread pool and they're all doing the same thing. We could be able to get away with it. If there is only one thread doing the job, then the system could just stop working because that kind of link in the chain of events that needs to happen to get the job done is broken and we can't do it anymore. Now, what a bunch of computer engineers figured out in one very, very amazing day is that you can turn computers off and on again, and usually that alleviates a lot of problems. Then some computer scientists decided to copy them because they were bored and decided they wanted to tell a computer to turn itself off and on again. And in the end, that was a really good idea that was a really good idea relative to the effort that it takes to implement it and the simplicity of the idea in the end. This, in some languages, this manifests in the idea of a supervisor tree. That we have a kind of graph like this one, a tree even, as the name says, of some supervisor threads, and worker threads. Usually the supervisors don't do anything and the workers do all the things, like they could be doing a messaging program. What a great animation. But then, when something goes wrong, the supervisor thread steps in, gets rid of that worker thread and replaces it with a new one. Now, the problem with this, in Common Lisp, is that, well, at least in our case, we didn't really write in a style where it was trivial to just replace these threads like that. Because we have global state, like we have all our tables that are shared by multiple threads to store networking information, and usually this supervisor tree requires a fairly actor-like style, in which we're just able to replace them willy-nilly. So we could construct a second tree to help us out with this. We'll call this a state tree, and it kind of looks like, in our case, in this diagram, it kind of looks like an upside down one. We have all these workers, and they depend on having some state objects that are shared between them, making sense. Say, for example, if this thread decides to stop working, and it was modifying this state, then this could just not make sense. And if that state doesn't make sense, then this object also might not make sense, and we'd want to replace both, if we want to replace that thread as well. So while this is also regarded by the people who do supervisor trees as something that you shouldn't really mess around with, and something that usually doesn't work out, we're going to try it anyway, because, well, any examples I can think of for why we'd try it out make us sound really terrible, so I'm not going to give any examples, but we're going to try it out. And for this, we need to imagine a kind of supervisor that could generate a sort of plan to reset the state and replace threads as necessary. Say in this case, we'll end up generating a plan that looks like this. First, what we're going to do is we're going to freeze the other threads that we have to take care of that are going to use this state so we can replace it later. Then, we'll remove this thread that's broken. After that, we'll then replace this state with a new state that does make sense. We'll unfreeze these other threads because they can start to use it, and we'll add a new thread to replace the old one, something like that. As well as this, as well as having to maintain state, we also have a difference in the way that we handle exceptional situations. In systems such as Erlang, they have a sort of philosophy called let it crash, and that sounds awful on paper. And basically what it means is that if something goes wrong, you let it go wrong, and you let the supervisor clean up for you, basically. In Common Lisp, however, you usually provide restarts and things like that that a client or a programmer could use to try and relieve the worker of the situation. So we want to try and integrate these two. So as well as this plan to replace state, we also probably have a plan. We want to generate a plan to bail out these threads. So we can imagine it works a bit like this. We have a supervisor here, the square, and we have a worker here, the circle. And we're going to draw messages sent by drawing arrows going from this line to that line. And as time goes on, we're going to draw the next one lower, and so on. So what could happen is that the worker sends the supervisor a message saying it's not working. And it gives it a bunch of restarts, or a bunch of ways they can get out of this situation. This is somewhat based on the debugger protocol that Robert Strand presented in his European Lisp Symposium talk about omnipresent debugging. And we'll have to say that we were heavily influenced by that. So we'll say that the worker sends the supervisor a bunch of objects representing how to get out. We could invoke a restart, we could have the thread restart itself, or if the thread's somehow corrupted, we could have the thread exit outright. Then we could have the supervisor look at a list of things that it should do. And it might say, we've already crossed it out, but it might say that restart the thread. We might tell it to restart the thread. Then, say it doesn't work again. Then we'll try something else instead. We'll say, tell the thread to exit and write a scolding email to me, because that's the only way I get things done. So we can see like that we can generate plans that integrate with a condition system and integrate with state. And by no means is it pretty, but by no means is it a pretty solution, but that's kind of what we have to do if we have to get out of ugly situations involving state and conditions. Speaking of ugly situations, we'll talk about some of the things that don't really work so well in Netfarm. Earlier I had mentioned the idea of having programs that handle side effects and presentations and things like that. This manifests in a system called the computed value system. Objects don't modify their data because we use a hash, and if we modify the data, then we modify the hash, and the object will basically not be itself because we won't be able to pick it up using the same hash. So instead, we have a section in the object's data for storing computed values which aren't hashed, and like I said before, can be reproducible and can be reproduced using a deterministic program. And basically the way it works is like this. When an object is introduced to a network, the node will run a program called the initialization script. And then that could possibly add some computed values to the object that sent it, or more likely is that it sends messages out to another object. So for example, if we had an object that was mutable, and we sent an object and we created an object that was designed to succeed it, then what we might do is we might have this object send a message telling the old object to add a back reference to it. Or in this case, the forward reference, and it has the back reference. But either way, we're adding another reference that wasn't there when the object was created. Then what the message receival script will do is it will look at the message, and it will look at the object that sent it, and decide if the object is basically allowed to say what it's just sent to it. In the case that it does, they will then go with it, and it will add a computed value. If it doesn't, then it doesn't do anything, and we've achieved some form of encapsulation by having the object have the final say. As well as having encapsulation, we also have a polymorphism, as we don't really care about what exactly the other object is going to do with this message. It could always ignore it could always add a computed value, it could do something completely different, it could just add a computed value with no relation to the object being that object that sent it. Anything could happen, but supposing that we have a common protocol, then we may have expectations of what should happen, but in the end, the object decides what goes. Well, that sounds really nice. We have a few problems. The first, and most important, is that to track these computed values, we theoretically have to run these sort of scripts for every object, because just looking at, say, hashes or anything metadata like that, we don't immediately know what objects are going to send what to what. So to do this, we do include information about messages in our metadata. Specifically, that we have nodes collude by listing objects affected by each object as part of the metadata when they exchange lists of all the objects which we use for synchronizing. Then the nodes can just retrieve the objects that affect the objects that they've decided that they want to keep. And they'll be able to track the effects like that. And it is admittedly quite messy to implement. But we are rewarded with a very pleasant system for doing access control and maintaining many different types of objects. So, to put this into perspective, I'm going to give an example of another idea that was given. Say instead that we use some kind of query language to represent these kind of things where we might have back references. Could we say query for an object that references an object that we have already? First off, we have the problem that we'd have to implement this query language and do it efficiently. If you don't, say, use a relational database like a SQL database or anything like that, then odds are you'd have to implement half of one in order to implement the query language properly. However, we'd also have to factor in our ideas of access control and polymorphism as well. Access control could be doable, but the query language would have to be sufficiently complicated and sufficiently expressive to be able to represent many different forms of access control. So, say an object could be succeeded if, say, it has 5 authors. Say that we might have to have a majority. Say that 3 might have to have signed the replacement object. That could be quite difficult to describe in a query language. As well as this, we also miss out on the polymorphism, because the query language would have to be able to understand many different situations, and in a computed value system like the one we just described, many different scripts can be used in different objects that end up sending the same message, but for completely different reasons. So, for those reasons, our query language wouldn't really fit. And in the general sense, we almost are kind of stuck with an almost Turing complete system for producing references, because in the end we don't really know. We decided that we don't really know what kind of relationships that people would want to form between objects, and we don't really know why and for what, and what preconditions must hold. On the other hand, we probably will simplify the so-called actor system into something that resembles more of a remote call kind of system. The idea here is that, I forgot to add an arrow, the idea here is that when we initialize it, we'll have the initialization script, but instead, it will call a method on the other object, which will do what it pleases, and then it can choose to return a value. And the idea is that we can have this back channel as well, that will actually return a value. So we could, say, implement more functional values. Say we could have this object ask this object for its name, and then this object could decide what to do based on the name. Or we could have, say, this object tell this object to call a function with every element that contains, saying if it was a collection of some sort. So we can get into some very nice abstraction. We can get very nice abstraction happening if we had more of a method sort of calling system. But the phony actor system, I think was the working name for it, is sufficiently good to write quite a few programs. But, having a method calling system, or A method calling system would just take it and give us quite a lot more power. Now, of course, that wasn't really an actor system in the end, but someone called it an actor system, and I thought it was quite funny because it really wasn't. Because in an actor system, of course, this can send a message back, and we can decide what to do with that. And the other thing is that actor systems are sometimes non-deterministic, which is the exact opposite of what we want in order to be able to do reproducible side effects. Moving on, we have a few more nitpicks, and those basically deal with how we represent Netfarm stuff in Lisp and how Lisp and Netfarm talk. So, some little differences. Netfarm represents booleans as a different type using the keywords true and false, but Lisp uses a symbol, two symbols, that are basically picked at random, effectively. If Netfarm understood symbols, then there'd be no way to then we wouldn't really be able to distinguish between true and false and the other symbols, or any other meanings assigned to those symbols. As well as this, as I've also described, the Netfarm scripts are not written in Common Lisp. Rather, they're written in a script machine assembler. The assembler is based off the, what's it called again? The functional virtual machine that I mentioned that I thought was really cool in the last European Lisp Symposium. Or sometimes we write it in our scheme compiler or something like that. Point is, it's not Common Lisp, and so it really pokes out. And because of our access control, and because we have a multi-user system, it could also be a bit tricky to have generic functions. So we have methods attached to classes like Python or Smalltalk or any other language that basically isn't a Dylan, Julia, Common Lisp, Scheme with tiny C loss even, or any of those that do have generic functions. Using hashes to address the objects, we're stuck with early binding to some extent, which also is a pity. And right now, we can't forward reference classes because we want to be able to look up a class before the client has actually instantiated it, so that we can receive an object off the network and then find the class that we have to pick for that and then use that. But that is just an implementation detail, more like a bug, and we can probably defer finalization so that we can have forward referencing, and then only finalize when it can be finalized, and hopefully we can work that out. That's the least important part. The most important parts are that we kind of have problems with Netfarm representation versus Common Lisp representation. Actually, I think Robert told me off for that, and I'm going to have to work on figuring out how we can make that work. But my current hunch is that we'll basically supply each slot with a function that can convert from whatever's suitable for Netfarm to whatever's most appropriate for Common Lisp, the client in Common Lisp, and vice versa. That basically sums up all the stuff I have to say about Netfarm and concurrent programming and distributed programming and all that kind of thing. So to summarize, we have a set of loosely coupled and extensible protocols that allow for very productive development of networking systems. What we have might not be very good, but you should be able to reuse large components of it in a new distributed object system. And of course, we write Netfarm in a way that we assume that everything is going to get thrown out and replaced eventually, which basically forces us to think makes us work in a very abstract manner, which makes things very replaceable. As well as this, it's very possible to filter our content in a distributed manner using our peers and some simple statistics. And with some helper libraries, we think that you can have some confidence that you've produced robust and performant concurrent programs in Common Lisp. So, here are some links that might be interesting. We have a specification of sorts. It's not quite done, actually, but it might or might not help give you an idea of what Netfarm can do and how we do it. You can also retrieve the demos. Now, these admittedly aren't done and quite messy because I've had very little time outside university and other stuff in life to write the demo and the presentation. So I'll probably add another demo as well that works based on our decentralized 2 message protocol as well. But for now, we'll just have the recommender and I'll clean it up eventually. As well as this, you're very welcome to lurk and or discuss the Netfarm system on Freenode or Matrix with those channel names. So, thank you very much for sticking around, and I'll see you all later.